Okay, so this is our first MRI talk. This is just an introductory talk, going to cover some of the basic principles and introduce some of the vocabulary. The first vocabulary word that I want to introduce is this idea of an active nuclei. So here's your standard Bohr model atom where you've got your protons and neutrons in the middle, orbited by electrons. This would not be an example of an active nuclei. Now, why is that? Because there's a balanced number of protons and neutrons. For a nuclei to be considered active, you need an odd mass number. In other words, the number of neutrons slightly more or slightly less than the number of protons, so that your spins are not equal and opposite. In other words, 2 up and 2 down, or 1 up and 1 down, or 4 up and 4 down. If you've got an odd number, no matter what your combination is, there's going to be some net spin in one direction, which makes it active. Now, here are the examples of some of the more common things that, these are the elements that can exist that will obey this rule, and the majority of these exist at some concentration in your body. This one, obviously, is the one that's most commonly used. So why is hydrogen so good? Well, 1, it's odd, so it will spin. And 2, it's everywhere in the body. It's in your brain, it's in your liver, it's in your feet, it's in everything. It's better to think about these little hydrogen atoms as tiny magnets, maybe something like this. And normally, when in the absence of an applied magnetic field, the hydrogen nuclei are just sort of randomly oriented. Then when you apply a magnetic field, you're going to have a certain percentage of them line up with the field. This magnetic field is going to be referred to as B0 in all your MRI textbooks and MRI lectures, and in the multiple choice questions that would be asking MRI questions. But let's not get it twisted. The magnetic field is not ripping your hydrogen atoms around your body. The hydrogen nuclei themselves don't move. It's the magnetic movement that aligns. So something sort of like this. And then when you apply your magnetic field, it orients in that direction. So, like that. Now notice that some are pointed up and some are pointed down. They're not all pointed up. So there is going to be a majority of them pointing up. And this small excess that line up parallel to the B0 constitute the net magnetization vector, like that. So all these small ones are sort of thought of as one big one with an arrow. Now this is going to change depending on the field strength that you use. So if you have a 0.5 Tesla magnet, you're going to have a slight majority directed in the direction of the field. Or if you use a 3 Tesla magnet, you're going to have a larger majority. So the magnitude of the net magnetization vector is larger at high field strengths relative to low field strengths, and therefore you have more signal. So these things process around the magnetic field, or in direction there, and this path is called the precession path, and the speed at which they wobble around B0 is referred to as the precessional frequency. That thing. It's important to be able to calculate this precessional frequency, which I'll get to in a minute, why. But if you were wanting to calculate it, or just understanding the relationship, you would never be asked to actually calculate it, I wouldn't imagine. But knowing that it does get calculated is useful. So the way it's calculated is that the strength of the magnetic field, be it a 1.5 Tesla or 3 Tesla, etc., is multiplied by some random constant for hydrogen. And this is referred to as the Larmor equation. Now, this constant for hydrogen is different than would be for carbon or fluorine or whatever. But this allows you, or us, to specifically image hydrogen and ignore all the other active active nuclei in the body. An important relationship that I want to point out here is that the more of this that you have, the faster your precessional frequency is going to be for the specific element that you're imaging. So who cares? You care because of this idea of resonance. So nucleus gains energy and resonates if the energy is delivered at the exact same precessional frequency. If the energy is delivered at a different frequency than the Larmor frequency of the nucleus, you can't get resonance. In other words, you won't be able to image it. So how do you know how to deliver or when to deliver your energy so that you can image the thing you want to image? Think about it as trying to push somebody on a swing. You have to know when to push them, right? You don't push them as they're, all the way out into the swing. There's a certain time that you push them to sort of maximize it. Or another way to think about it would be if you were running beside somebody and you wanted to hand, or if you wanted to hand something to somebody and they were running, you would have to run at the same speed to be able to hand it to them. So something like this, all right? So here's our hydrogen, and we want to deliver something to it here, so we're going to wait, we're going to push it, and you can see, there you go. So this RF pulse is sent at this specific Larmor frequency, and it's timed so that it gets that maximum push. So what is an RF pulse? It's basically radio wave. Now remember that this kind of these kinds of waves are non-ionizing. You're not getting ionizing until you get all the way over into this kind of bandwidth. So let's talk about the first result of resonance. When you apply an RF pulse that causes resonance to occur, this is called excitation. So the absorption of energy causes an increase in the number of spin-down hydrogen nuclei populations, as some of the spin-ups gain energy via resonance and become high energy. The difference between the two populations corresponds to the energy required to produce resonance. As the field strength increases, the energy difference between the two populations also increases, so that more energy, or higher frequencies, are required to produce resonance. In other words, it takes some of the hydrogen atoms that are directed in the opposite direction of the magnetic field, well, some of the hydrogen atoms that are directed with the magnetic field, and flips them so that they are directed against it. Sort of like this. See that? See how we had change? And notice that less of them changed at a higher field strength relative, if we use the same pulse, relative to this one, so more of them here. So the first result, or consequence, is that the net magnetization vector moves out of alignment with B0. This occurs because some of the low energy nuclei are given enough energy to join the high energy population, high energy being the ones that are directed in opposition of the magnetic field. As the vector, or the NMV, reflects the balance between low and high populations, the resonance causes the vector to no longer be in parallel with B0, but instead be at some certain angle to it. Now, the angle to which the net magnetization vector moves out of alignment is referred to as the flip angle. And this depends on both the amplitude and the duration of the RF pulse. So what does that mean? It means that because more of them are pointed away than are pointed with, you've got your vector that is now also pointed away. This would be in alignment, this would be away. So small arrow is only going to have a small flip angle. Notice that it's only coming down to about 30 degrees. We'll run this again. See where it's going? Stops right about 3 o'clock. No, 2:30? 2:30. Stopping right about there. That's a small RF pulse. What about a big one? All the way down to 90. See the difference? So flip angle depends on the amplitude and the duration of the RF pulse. So more and more and more of those little hydrogen magnets turned in opposition of the magnetic field with a bigger pulse. That makes sense. So here's some vocabulary. When your B0 is termed the longitudinal plane. So things that are in alignment with B0 are in the longitudinal plane. The plane that's 90 degrees to B0 is referred to as the transverse plane. And the thing in the middle, basically, is the flip angle. And it can be flipped all the way down into the transverse plane, like at 90 degrees. And when it's aligned, then there is no flip angle. So what is the second result of resonance? The second result of resonance is that the magnetic movements move into phase with each other. Phase is the position of each magnet, or each magnetic moment, on the precession pathway. They're either coherent, in other words, they're in the same place on the precession path at any given time, or they're out of phase. So in phase is when they're coherent, out of phase is when they're incoherent, and they're not in the same place. So these two guys would be out of phase. They're not at the same place at the same time. But this is the second side effect of resonance, is that they line up and they become in phase. So the first result of resonance is that basically you create a flip angle where more of the hydrogen atoms become out of, they have an opposite direction to the magnetic field relative to what they were before. And the second result of resonance is that the hydrogen atoms begin to move in the same precession. They become in phase, whereas their normal relaxed state is to be out of phase. So what's the difference between phase and frequency? Frequency is how fast they're moving around, or at what speed they're moving around. Phase is where they're at on their path. Either they're together, in phase, or they're not, out of phase. So this would be in phase, this would be out of phase. Alright, so all that's great, but how do you actually produce a signal? When the transverse plane is coherent, or in phase, and perpendicular to the coil, this is when you have signal generation. It's sort of like running next to somebody who's running at the same speed. You can't measure how fast they're running. It's like an Einstein relativity thing. They have to turn and run away from you for you to measure that speed. So here we go. We got knocked down. And now that we're in this plane that's perpendicular, we're starting to put off signal. So something like that. So back to this, let's start to, so things start to work backwards. In other words, there's a period of recovery where we started out here, and slowly these things, as they lose energy, and then we lose a little more energy, 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 and now we've recovered. In other words, we have returned to being in the same, net magnetization vector is in the direction of the magnetic field. And this is referred to as T1 recovery. Recovery in the longitudinal direction. Now, we've been lined up here. Let's turn this thing up so we can see it a little better. We're lined up here and we're processing in phase. And then over time, we're going to lose energy so that we're becoming less and less and less in phase, and now we're totally out of phase. This is the natural state of things here. And this is referred to as decay, that is occurring in the transverse plane. So as magnitude of the transverse magnetization decreases, so does the magnitude of the voltage induced in the recovery coil. In other words, less and less and less signal is being produced, and this reduction of signal is referred to as free induction decay, or FID signal. The decay in the transverse plane, this kind of decay, where it's becoming less and less and less in phase, is T2 decay. So T1 is the longitudinal, T2 is the transverse. So this is another way to look at T1. This is the kind of drawing that you'll often see as a T1 curve. So we start out here where we've been knocked completely down. We're no longer in the path of their net magnetization is no longer in the path of V0. We've been hit with that pulse down to 90 degrees, and then we start to recover. Recovering, 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 until we reach a point where the net magnetization vector is back in phase with V0. Something like that. Now, T1 recovery is the result of nuclei giving up their energy to the surrounding environment. Some people will call this a spin lattice relaxation. Energy released into this lattice causes the magnetic moments of the nuclei to recover their longitudinal magnetization, in other words, magnetization that's in the longitudinal plane. The rate of the recovery is an exponential process, with the recovery time constant, or T1, is defined as the time it takes 63% of the longitudinal magnetization on the tissue to recover. So in other words, right here, that's T1. Now let's look at T2. So everything is in phase, processing in phase, and we're going to slowly become more out of phase as we lose our energy there. Something like that. T2 relaxation is this loss of coherent transverse magnetization, and it occurs because of interactions between the magnetic fields of the adjacent nuclei. They don't like moving together. Some of them are repelling each other in different directions, and this is called spin-spin relaxation. So instead of giving away energy into a lattice or thermal loss, T1 like the thermometer, it's this interaction between each other, the spin-spin interaction that causes this T2 decay. And the rate of decay is also an exponential process, so that T2 relaxation time of a tissue, as far as the constant of decay, is when it takes 63% of the transverse magnetization to be lost. In other words, 37% remains. So what causes protons to lose their transverse sync, or their, what causes this T2 relaxation? The first thing is inhomogeneity in the external field. And the second thing is inhomogeneity in the local magnetic field, the stuff that's actually within the tissues. Pure things like water are have less inhomogeneities in them, so they will take longer to decay because they have less inhomogeneity within the actual tissue, and are therefore bright. So that's why water is bright on T2. If you think about it as being completely clean, it has less of these inhomogeneous interactions. Now, the signal of T2 decays faster than people who do complex math to predict these things thought that it would. And the reason is that their predictions are based on tissue spin interactions alone. So just that second part. And for this reason, the math falsely assumes that the main external field is absolutely homogeneous. It is not. The field is heterogeneous, and because of this, you've got additional interactions which further speeds the decay. So there's this idea of T2 star. T2 star is tissue spin interactions, like the interactions within the tissue itself, plus field inhomogeneity. A pure T2 is just your spin interactions within the tissue. Now, because the inhomogeneity exists in this field, T2 star is always faster than T2 because it's 1 plus 2 instead of just 2. So is there a way to fix T2 star and make it just T2? Sort of, but let me define some terms first. Got our different RF pulses here. The time between the initiation of each RF pulse is referred to as the TR, or the repetition time. You'll hear that terminology. I'll use it throughout the lecture series as a TR. What that actually is the time between each pulse. Now, here's another sort of diagram of what's actually happening. Here's our free induction decay as the, without any magnetic gradient, this is a received signal. So there's also this entity called an echo. And think about that as you've gone into a tunnel and you shout, and your voice trails off, and then you start to hear your voice again. It sort of comes back. That's the echo. So what is the TE, or the time to echo? This is the time between the middle of the 90-degree